can tell us about, I think, a combination of quite a sequence of work in graph algorithms.
Thank you. I guess I'm audible throughout. All right, so thanks, Tom and Ramanujan for inviting me to this wonderful workshop, really. I'm going to talk about graph algorithms today, and this is an area of research that I'm exploring for the last couple of years with a fantastic set of co-authors, including Joakim, Jan, Yuval, Troy, Simon, Pawel, Michal, Andrés, and of course Danupon, who is sort of like a constant co-author in all those papers. Okay, so what I'm going to talk about, I suppose, can be like motivated in many different ways. And usually what I do is that I try to tell a story of victory in the sense that we have designed this algorithm, we have designed that algorithm. But today I think that it would be better to tell a story about our inadequacy, and so that you can have some food for thought along with the lunch as well. We need two things to begin the story, and I will just give a very short primer on them to get them out of the way so that we can go into it. So the first one is communication complexity. I'm sure most of the people, I know for a fact that they know what is a communication protocol, but this is just a primer. So the model is a two-party model where we have two players, Alice and Bob, and they have input distributed among them. Alice gets X, Bob gets Y, but the function they want to compute depends on the joint input X and Y. So the only way they can do it is to communicate. And we will also assume that they have access to shared randomness. We can also think of a private randomness model, but these things are sort of equivalent. At the end, after the communication, interactive communication, we want both of them to know the answer. That's the model. And the measure of complexity in this model is the bits that Alice and Bob communicate among themselves. So I will try to give you an impression how powerful this model is, as well as how inadequate this model is, by a simple situation where you have Alice has a set X, Bob has a set Y, and they want to compare these two sets. So on one extreme, if you want to think of like Alice and Bob want to check whether these two sets are the same, which means X is equal to Y, if you have shared randomness, then you can just do it by communicating 8 bits, irrespective of the length of the set. Yeah? And this is where the power of randomness shines through. And it uses some clever ideas about hash function and error correcting code. On the other extreme, if we want to check whether Alice and Bob sets are very different in the sense they do not intersect at all, then it's very hard for communication protocol to do. This is called the set disjointness problem, and this is sort of the poster child of communication protocol. And there is nothing known better than Alice sending everything to Bob or Bob sending everything to Alice. There's always this trivial protocol. Okay, so why this is interesting? Because here we can prove unconditional lower bound in contrast to sequential model. And partly because of that, it is extremely useful in other models of computation. And here is just a very sundry list of them. There are many more. And the idea is that because you can prove unconditional lower bounds in communication complexity, that sort of carries through to unconditional lower bound in all of these systems. So which is why communication complexity is a very good tool to prove lower bounds. But for today, I'm going to impress upon you, it's also a very good tool to design an upper bound as well, in the sense, because communication sort of captures the core hardness of the problem, it would be a good idea to first design an algorithm in the communication setting and try to implement that algorithm and modify some of the parts and the subroutines of the algorithm to implement in other models of computation. This is sort of like a top-down design. And the good thing about it is that if you can do it, we are not sure you can do it. If you can do it, then you have one schematic algorithm that works in many models. Yeah. Of course, we are not it's not obvious that we can actually do it for any problem. So I'm going to tell you today about 2 case studies where you can do it. And for those 2 problems, let me just introduce the second notion that we need in today's lecture. It's called submodular set function. Again, I'm pretty sure everybody knows over here what is a submodular function, but let me just give you a brief overview of it. So these slides are taken from this excellent slides by, which is over here. So what is a submodular function? Before telling you what is a submodular function, let me tell you what is a set function. So think of a set, a ground set. You can think of it can be a set of many things. I just given you a menu from your favorite fast food restaurant over here. And a set function is a function that is from the power set of that ground set to a real number. Think of it as a cost of buying items. Okay? That's a set function. When a set function is submodular, the best way to remember this is to think of the US style like McDonald's function. In the sense, if you have chips, then if you want to add a drink to it, the amount that you have to pay is more than if you have cheapened drinks and you want to add another drink to it. Yeah? So this is sort of the law of diminishing marginal return. And this is a very useful law, and it's like prevalent in many different areas of society, to be very honest. And there is an equivalent formulation of this, which is written like this, which is to say that if you have 2 sets S and T, and if you look at the value of the submodular function on those sets, add them together, that will overestimate the function when you compute it on the union and the intersection and add them together. This is why the name submodular comes along. If it is equal, it's called modular. If it is the other way around, it's called supermodular. So any linear function is a modular function. That's one of the things that is good to know. All right, so you have this submodular set function, and it's ubiquitous in many different areas, and everywhere it's a very deep and wide area of study. However, in today's menu, we have network design on it. So we're going to look at 2 things. One is the asymmetric version of this submodular function. And again, it's very well instantiated by the global min-cut problem. And another version is the asymmetric submodular function, where we look at the bipartite matching. So these are our 2 protagonists today. OK, so before going into that, let me just try to impress upon you why the cut function is a submodular function. So you need to define a submodular function. You need a set, a ground set. Here, think of the ground set as a set of vertices. And also, you need a function from the power set. So given any subset of the set of vertices, you're going to associate the cut to be the value of the function, the value of the cut to be the value of the function evaluated on that set. And to prove that it's a submodular function, you need to show that this holds for any set A and B. So that's not very hard to see. So think of this A. This is a cut. And the edges that are cut by this is the edges that is crossing the dotted spline. And you have another set B. And if you look at the A intersection B and A union B, you see that everything on the right-hand side, all the edges that is cut in the right-hand side is also cut on the left-hand side. But this red edge, which is going from B minus A to A minus B, is not counted on the right-hand side. So this sort of immediately tells you that this holds, and you can also convince yourself by just counting it. You will see the left-hand side is 10, the right-hand side is 8. Left-hand side is 10 because this edge is counted twice, where this is not counted over here. So that's why it's a submodular function. Now, because we have the cut is a submodular function, let's try to look at 2 versions of this cut. One is a symmetric version. So we know this is a very obvious thing to state, that if you look at the set of vertex set A, the cut value associated with it is exactly equal to the cut value associated with the complement set of vertices. So which sort of inspires us to define what is a global min cut, in the sense you have to come up with a cut which is the minimum value over all possible cuts. And because of the stupid thing that the symmetric submodular function has, that it will always minimize when the set is empty or the full, we need to look at a cut which is non-trivial, in the sense it's not a cut where one side is empty. Yeah, that's called a non-trivial minimizer. Whereas in the asymmetric version, think of it as ST min cut. Yeah. So now, even if this set A is now just the set of vertices on this oval, and you see that the cut of A, cut value associated with A, is not exactly equal to the cut value associated with V minus A, right? Because when you're looking at the cut of A, you're also including S into it. So that's the blue cut. When you're looking at V minus A, again, if you include S into it, you are counting both the blue and the red. So they are not the same. This is the asymmetric version of it. And the problem that we're going to look at is bipartite matching, which sort of reduces to max flow. So it is an asymmetric submodular function on which we want to solve something. Okay, so what about the models of computation? So the usual model to study over here is the query function, in the sense you have an oracle to which you just query what is the value of the submodular function on this set, and it will give you the value, and you want to minimize the submodular function. So for graph cuts, it's good to just think of it as like you are allowed to ask cut values, because this is called a cut query, and the goal is to minimize the number of cut queries. One of the useful properties to note for submodular function is that if you have two submodular functions and you add them up, that also remains submodular. And that gives us the idea of this, thinking of this problem in a two-party communication model as well, in the following way. So think of a graph. Some of a bunch of edges is given to Alice. The rest of it is given to Bob, and this is like a balanced distribution. Now, just the edges of Alice defines a cut function, which is submodular. Think of it as FA. And the rest, same for Bob. He also has a cut function, which is FB. And the actual cut function of the graph is defined as a sum of these two cut functions. And so you can think of it this way, and you can ask, give me the minimum cut. And you have to minimize the number of bits communicated. So this is the setup of the problem. And let's see what is known about it. So submodular function, this is known for a very long time, that you can actually extend it to a continuous version of it by something called a Lovász extension. And then you can solve it by using the tools of continuous optimization, especially convex optimization, and you get an n-square query runtime. For symmetric submodular function, where you are not just allowed to have just the minimizer, you have to output something called the non-trivial minimizer. It's not obvious whether you can use this to output a non-trivial minimizer. This will give you a minimizer. It can very well give you the empty set for symmetric submodular. But there is a way, and this is first observed for cut functions, something called isolating cut. And this isolating cut, think of it as a black box which uses the ST version of the symmetric submodular function to give you a non-trivial minimizer, and it maintains the runtime, query time, query complexity. Again, n squared. So that's the state of the art when it comes to upper bounds. However, the lower bound situation is appalling, to say the least. We have an omega n randomized lower bound from 2008, deterministic omega n log n lower bound, which is a recent paper in Fox this year, And that's about it. So there is a huge gap between the upper bound and the lower bound. So the question you might ask at this point is, can you think of a problem which can be conjectured to have a superlinear lower bound? Yeah? So we are going to answer this question partially and negatively today. In the sense, we are going to tell you some very immediate candidates that are not good. So it seems like a negative answer, but while, like en route, I'm going to give you some algorithms which are also very exciting. Yeah? But this is the motivation of the whole project. Let's put it this way. So the case study 1, and this is on minimum cut. How much time do I have? 20 minutes. Okay. So minimum cut. So let's just define the problem. You have a graph. A cut is, you already know, it's just a set of edges whose removal disconnects the graph, and the min cut is the cut with minimum total edge weight. Yeah? And the goal is to find a min cut in a weighted graph. For the timing, let's just skip this word weighted. Let's just look at simple graphs for now. Okay, what is known? 2008, Harvey shows that it can be done in n log n cut queries. And very recent work by Rubenstein, Schramm, and Weinberg, it shows that you can actually, for unweighted minimum cut, can be found out in n log qn cut queries, which is very close to connectivity now. The lower bound is hanging over here, n over log n. And we can, for all intents and purposes, we can think of it as omega n, and it just uses a communication complexity conjecture of Bawel, Frankel, and Simon. However, if we allow, if we are looking for min cut, not connectivity, you can have slightly improved lower bound. Still sublinear. So the question comes as like, what is the exact complexity? Can we even use this function to prove a superlinear lower bound? It's a very recent result of ours. We show that no, it cannot. Edge connectivity needs an order, just order n cut queries, and that's enough. Okay, so this is one of the first negative news, that you cannot use edge connectivity on simple graph. So let me just give you, let me just take 2 minutes to give you the idea of how it works. I think it is fairly interesting and very cute idea. It uses two things. One technique is called star contraction. The other one is called separating matrix. I'm going to skip this one. I'm just going to talk a little bit about the star contraction because it's like a fairly a non-specific technique. So here is the main idea. Think of a graph, and let's just seize the min cut over here. Now, if I have every vertex choose a uniformly random neighbor of it, yeah, and S, let's say S is the set of sampled edges that I have chosen, it's not very hard to see that you will very rarely cross the min cut. Why? Because think of a vertex. Think of the edges that is incident on it, that is crossing the min cut, and the other side, those edges which are not crossing the min cut. It's obvious that the number of edges that is crossing the min cut is always at most the number of edges that is not crossing the min cut, because otherwise you can just move the vertex to the other side and you have a smaller cut, right? So that's just give you, with at most half probability for every vertex, you're going to cross the min cut. So if you can sort of like work on this technique and show that if you do it for all the vertices with constant probability, you are never going to cross the min cut. And there is a recent result by Ghaffari, Nowicki, and Michal Dory, which shows that not only it will not cross the min cut, if you do it once more, you will also can reduce the number of vertices to n over delta, where think of delta as a minimum degree. This was an extremely cool idea, and it just works very well in many different models of computation. except cut query. At least we do not know how to make it work. So what we did was we just stayed at this protocol for a while and thought that how we can make it work for cut query. Let's look at all the techniques that we know for cut query and which of them we can make it work. And turns out that a very a simple modification of this protocol will just work. It's instead of every vertex sampling one random neighbor of it, first pick a set of vertices, let's call that set R, and every vertex chooses a uniformly neighbor inside R. That's it. Now again, the thing that I mentioned is like every vertex going to have less than half of its neighbor towards the min cut also holds when you restrict it to a random set R. So the techniques just goes through. You need a little bit more technicalities to deal with, but it works and it will give you an order n cut query algorithm for min cut. This and a little bit more. So that's the general technique I wanted to talk about. Now, given this, that for simple graph you cannot really prove anything superlinear, the question then comes is like, okay, let's just put weights on the edges and let's see whether you can prove something superlinear over here. The answer, just a bit of foreshadowing, of course, because I'm mentioning this problem, which means that we cannot really. What is known about weighted mean cut? This is sort of one of the fundamental problems. You can find it in the chapter 1 of the graduate textbook of randomized algorithm, right? And there are like two specific algorithms, which is very well known. One is the edge contraction algorithm by Kaga, and another one is what we are going to talk about today. The problem is that this is what is interesting to us, because this has almost linear in m. M is the number of edges. So if for a sparse graph, this is much faster than this guy. But the problem with this problem is this algorithm is that it uses dynamic programming and data structure, which is very hard to adapt to cut query algorithms. So this was the state of the art. And you see that I have put in many other models of computation over here. That's for a reason. So this was the state of the art before, let's say, 2020. So for sequential model, there is this Kargar's algorithm, and there is subsequent improvement on it. For cut query model, there is, we have already talked about this, there is an order n algorithm. For the semi-streaming, there are two-pass algorithm. There is a congest algorithm, which absolutely appalling constants over here. And there is a PRAM algorithm as well. And these things are red because they are all just for simple graphs. Nothing works over here for weighted graphs except Kargar's algorithm over here. What we did was we came up with one schematic algorithm, which is again looking at the communication complexity and then try to modify it for different models. And this gives you all the things. And most of them are state of the art. And it's published in 2020, and just within 2 years, most of these things have been simplified again. So I'm actually giving you something a little bit outdated. Okay, but the thing is that over here, this is what is interesting. This gives you an order n cut query algorithm even for weighted min cut. So if you want to prove superlinear lower bound, again, weighted is not the right way to go. I'm just going to give you a very basic idea about what is the common barrier, and then I'm going to skip to the second case study. So the reason all the improvements have been on simple graphs because of what I think of it is these two things. It just makes life easier to think of simple graph because you can do sampling and you have you have a control on how the sampling algorithm works because you have a control on the number of edges or the total weight of the edges. Yeah? But the Kargar's work for weighted, so what is so hard about Kargar's framework, really, to adapt it to other things? And that's one of the problems that he solves in his algorithm, which is called the two-respecting min cut. So the problem is the following, that you have a spanning tree. in addition to the graph, and you want to output a cut which cuts at most 2 edges of the spanning tree. Yeah, so this is two respecting min cut. The blues are the edges of the spanning tree. This is not. So now your problem changes to finding a min cut, from finding a min cut to finding a min cut which is 2 respecting a given spanning tree. And what we show, and what Kargar showed actually, that if you have an efficient algorithm for solving this 2 respecting min cut, then you have an efficient algorithm for solving min cut. And this is the main bottleneck. What we do is that we solve this 2 respecting min cut problem in the communication setting, which sort of just generalizes naturally to all the other models, except maybe distributed. It requires some work. But that will give you the schematic algorithm. So two takeaway messages from here. One is that it's a good idea to think about communication before designing more algorithms elsewhere. And the second one is like weighted min cut is not really your problem if you want to prove superlinear lower bound in the submodular function. Let me just skip to the second case study. I'll talk about a little bit about matching now. 10 minutes. Good. And especially bipartite matching. So the problem of bipartite matching is sort of like very well known, right? So you have a bipartite graph as an input, and matching is just a set of disjoint edges. Now, why I'm talking about bipartite matching in a lecture which is related to submodular function and cuts, right? Now, here is a reason. So the bipartite matching reduces to ST max flow. This is sort of the first algorithm you learn about how to solve the matching efficiently. You just use a max flow algorithm on it. Now, the ST max flow has a dual representation, which is an ST min cut. So in the dual space, it is an asymmetric submodular function, right? So the matching problem also has a dual representation. We are going to talk about it very soon, is the vertex cover problem, which also reduces to ST min cut. But the fact that ST min cut is an asymmetric submodular function means that you can now use all the techniques that is there to solve asymmetric submodular function to solve the matching problem, right? Via this thing. The problem is that the techniques that we know to solve asymmetric submodular function requires, first of all, order n square queries, which is no good because in order n square, you can sort of learn the whole graph and you can solve almost all the problems on the graphs if you have order n square query access. So we need something, either we need something clever, which gives you subquadratic algorithms, or we need to show that for matching, this is not possible. You need to know, if you're solving matching, it's almost equivalent to just knowing the whole graph, right? So before going into cut query, let's try to focus a little bit on communication complexity. What is known about matching? So again, the trivial that I mentioned is order n squared. This comes just because there is a way to solve asymmetric submodular function with this amount of communication, or there is a trivial m log n algorithm where Alice just send all the edges to Bob. There are m many edges, each requires log n bits of communication, m log n is the communication. So that's the trivial upper bound. You can do something better. You can look at the algorithm of Hopcroft, which has a sequential runtime of m root n, and try to see what happens if you try to implement it in the communication model. It will give you an n root n algorithm. So which is a good sign, because now we have a strictly subquadratic algorithm communication-wise. What about lower bounds? There's a very old result from 1988, but also a seminal work by Heinel, Maas, and Turan, which shows that there is an omega n log n deterministic lower bound and omega n randomized lower bound. Where is the answer, actual answer? That's the question, right? And it's especially important right now at this point because there is a recent breakthrough result on MaxFlow, which has a sequential runtime which is order m for all intents and purposes. It's actually m to the power 1 plus little o 1, but it's linear. It's a very recent result. So, which also means that you can solve bipartite matching in order m runtime sequentially. So does it mean that we can try something like this and try to just make communication complexity to be order n if we just implement that sequential algorithm in a communication setting? Well, as it turns out that I do not know how to do that. There is maybe a way to do it, but that algorithm uses some fairly complicated continuous optimization techniques, which I don't know how to implement in communication setting. However, I know some simpler continuous optimization techniques, how to implement them, and what I will show you that is enough to give you a very efficient algorithm for matching. So just to let you know that this question, the closing the gap, is open from 88 essentially. Yeah? And we show that yes, we can close the gap. We will give you an order n communication algorithm. Okay, so how do we go about it? So we look at the linear program. So this is the linear program for matching. It has got edge variables, and each there is one constraint for every vertex. So there are really n many constraints, but the polytope that you're working with is of dimension n squared, possibly. Yeah. We can try to work on this polytope, but what we do is that we do not entirely work with this polytope, we work with the dual polytope of this. And why, it will be obvious in a few seconds. So this is the dual polytope of matching. These are the vertex variables. This is just a linear program for minimum vertex cover. So you have a vertex variables now, and you have a constraint for every edge. Now, it's sort of like, if you're paying attention, you will see that now this is a very interesting way of looking at the problem, because in the communication setting, what we have is that Alice has some of the edges, Bob has the rest of the edges, which means that in this setting, Alice has some of the constraints, and Bob has the rest of the constraints, right? Constraints are very nicely distributed between Alice and Bob. One of the reasons why we choose to work on this dual problem. And there is a theorem of Koenig which shows that if you have a maximum matching, the size of the maximum matching is f, if and only if it has got a minimum vertex cover of size f. This is just LP duality, but it has a name for it. And instead of finding the maximum matching, we will now try to find the minimum vertex cover. So if we can find a minimum vertex cover of size f, that is a certificate that the matching cannot be of size f plus 1, right? That's from the duality. So that's a decision problem. So we can now think about the decision problem, which shows that, well, here's a graph. Is the maximum matching is of size f plus 1 or not? That's a Boolean function, and we want to solve this. So that becomes a feasibility question, and you see that I have changed these constraints a little bit. There was an f already, and I have added a bit of slack. First thing to note that this doesn't really change the solution of the problem, because it's always a natural number that comes as a solution of this, but there is a reason why we change it. By the way, this communication complexity of linear system and program, this is not started by us by any means, but it's fairly new areas of study. And a good place to start is a very recent paper of Vimpala, Wang, and Woodruff in SOTA 20, where they look at the exact problem, but in a much more general setting. They don't look at one specific LP, they look at any general LP, try to solve them. But we are looking at one specific LP, and we solve it by cutting plane. So here is the polytope where we are working with. We try to find the center of gravity, and we try to find a violating constraint of it. And we go either left or the right, depending on which way the constraint is getting violated, and so on and so forth. That's how it works. These are cutting planes, and the thing to note over here is that each cutting plane over here is just an edge constraint, which means that Alice and Bob can actually find the edge which is violating, because the edge is completely contained with either Alice and Bob, and just transfer the edge across. And they will in sync in computing this, in doing this cutting plane method. So sending an edge across requires log n bits of communication, and by a theorem of Grunbaum, it shows it can be shown that this process terminates in order n steps. So order n rounds of communication. In each round, you have. So I'm going to skip this one because I'm sort of running out of time. So the point is that order n communication, and in each communication round, Alice and Bob just needs to share one edge among themselves, which requires log n bits of communication. So you get like linear communication, order tilde n. Okay, so that's for communication. Now, what about cut query? That's why we started, right? So it can be shown that this communication protocol is good enough to give you many other query protocols. One of them is quantum edge query, where we actually can improve the runtime to n to the power 1.5 from n square. We also can do OR query, and this is what is important to us. OR query means that you are allowed to ask a set of potential edges to the oracle, and the oracle is going to give you whether one of the edges of the potential edge present in the graph or not. That's a very general kind of query. So in that query model, we can show that same procedure is going to give you an order n log square n protocol. And this was the previous record was n to the power 1.5, and again, this is tight. There is a lower bound, which is n log n. Once you have this, you can tie your hands a little bit more and try to look at independent set query, where you have the query is two sets, one set from left, one set from right. Left set is x, right set is y, and you want to check whether there is any edge between the set x to y, or the xy is an independent set or not. This is a weaker version of OR query, but even in this query model, we show that this can be done. Same query complexity. And so once we have this one, we can show that cut query can simulate this. So cut query complexity is also n log square. Right, so this is sort of the bad news that we have right now. Okay, so two very specific problems, bipartite matching and cuts. And when I'm saying bipartite matching, this is for weighted bipartite matching even. You cannot prove a superlinear query complexity for some modular function. So what are the functions for which actually we can think of proving? And that brings us to my open problem section. And I'm just going to give you 4 things that I'm thinking about right now, and that will be the end of it. So the first is what I think is an exciting area of looking at is graph problems in two-party communication. And just this, no other motivation. I think communication complexity or two-party communication complexity is fundamental enough to for us to study many graph problems, and especially in the fact that The computation that we increasingly looking at is a distributed model of computation. So the sequential algorithms that we had previously sometimes fall very much short of getting adapted to distributed models, and communication complexity is one of the first things you should look at when you're looking at distributed graph problems. That's one of the things. And here comes the two things for which I think it would be hard to prove linear upper bound. One is the directed min cut, which is also submodular function, asymmetric submodular function, and vertex connectivity. We are working on it, but we are, I think, pretty far away from proving anything. So if you have any idea of what you think is the right bound for these two problems, I'd be very happy to know. Which, again, for SFM or submodular function minimization, graph problems are not the only problems. There are a myriad of problems which are also submodular function. So is it a possibility that other than you can find a problem which is not a graph problem for which you can prove high lower bounds? Something is known in this line. Even for non-trivial minimizer and omega n square lower bound is known for this line, but that problem is very unnatural. So what I mean over here is that is there a natural way of defining submodular function for which, for that class of function, you have a very high lower bound? And the last is round versus communication trade-off. And this actually brings me to the point of why we are studying matching. The matching is just an excuse to study max flow. Let's put it this way. We do not know how to approach max flow, which is why we are looking at an easier version of it, bipartite matching. And we have plan. Well, the plan was to, okay, let's just try to solve it and try to extend these techniques to max flow. Doesn't work. The technique that we have just doesn't generalize to max flow. So when you cannot prove an unconditional lower bound, the second step is to look at round versus communication trade-off. And even for reachability, which is the easiest version of max flow, we do not know how to prove anything better than log n rounds, let's say. Yeah? We have some lower bounds, but the lower bound just vanishes for when the round goes to log n. So anything that does not depend on log n, well, I mean, if you can break this log n barrier, that would be very useful, even for reachability, and I think it will give you some lower bound even for distributed models of computation. So that's where I will stop. Thank you very much.
Questions? So while you're thinking, maybe, so when we're thinking about lifting communication complexity, there's often generic type of frameworks. You mentioned the Blaise et al. Type of characterization. They tell you if you have a certain property and it satisfies conditions 1 to 4, then you can always have lift the communication complexity lower bound to testing. So when you mentioned this framework of first designing the communication complexity upper bound, then do you have any framework, something which is general in the sense of,
This is one of the questions. No, that's a very good question. Thank you. But we have been trying to formalize this notion. And so far, I think we have very little data points to actually come up with a formalization, which is one of the reasons we want to solve as many problems that we can by doing this and try to extract out a formalization out of it. But thank you.